Hi everyone, welcome to our next master lecture in the GoFly Master Lecture series. It's my pleasure to introduce Gwen Leiter, CEO and founder of GoFly.
Hello everyone, and thank you for joining us today. We have a very exciting master lecture for you today with Dr. Irene Gregory. As you all know, GoFly's grand sponsor is Boeing, and we are supported by Pratt & Whitney as our corporate sponsor, as well as several in-kind sponsors who directly support our GoFly team. In addition, we are joined by over 20 different aerospace and STEM organizations around the world to bring you this GoFly programming. And today we are very pleased to be able to welcome Dr. Irene Gregory, who is the Senior Technologist for Advanced Control Theory and Applications at NASA. Dr. Gregory's current interests are in the areas of robust autonomous systems, self-aware vehicle intelligent contingency management, acoustically aware vehicles, and resilient control for advanced unconventional configurations, with a particular focus on urban air mobility. Previously, Dr. Gregory's research spanned all flight regimes, from low subsonic to hypersonic speed, and included advanced control for aircraft and launch vehicles, aeroelasticity, fluidic control effectors, and autonomous vehicles. Her research has been documented in over 100 technical publications in peer-reviewed journals and conferences, invited lectures, and presentations. Dr. Gregory earned a bachelor's degree in aeronautics and astronautics from MIT, and a doctorate in control and dynamic systems from the California Institute of Technology. She is an associate fellow of the AIAA, a member of IEEE and IFAC. She serves on IEEE Control System Society Aerospace Control Technology Committee and on IFAC's Aerospace Control Technical Committee. She is an emeritus member of the AIAA Guidance, Navigation, and Control Technology Committee and a former member of the AIAA Intelligence Systems Technical Committee. And so without further ado, we are very pleased to welcome Dr. Irene Gregory from NASA to give today's master lecture.
All right. Guess everybody can see my screen.
All set.
So welcome. I'm going to give a brief lecture today on some flight control fundamentals and how they can enable safe flight of quiet, near VTOL personal flying vehicles. Very briefly, I've had an opportunity to work on a number of very interesting projects in my career. Pictures of some of them you see on this slide. So because of just the number of variety of experiences, there's a few things I've learned during my career, and I'd like to share with you some of those lessons learned. The control field itself is a vast control field. Discipline and flight control has been going on since the Wright brothers in 1903. So it's way too much information to give you even a glimpse of what's out there. What I would like to do today is I'd like to give you the fundamentals and essentials that will help you design systems to enable the flight of some of the new configurations that you're all developing. So briefly, we're going to give a introduction and what constitutes control of autonomous flight. Then we're going to talk about the importance of vehicle dynamics, some fundamentals of flight control, both analysis and design. I'm going to provide you just a few typical control methodologies that were used for flight, and then I'm going to leave you with a slide of references that should give you a really good starting point of where to go as you need to learn more in order to actually design control systems. So without further ado, when we say controls actually is more than just moving surfaces on the vehicle. Controls entails the entire vehicle management system. You have to do it, especially whether it's autonomous flight or it is piloted flight of some sort. You need to be able to do pre-flight system diagnostics, trajectory planning, there's mission management that incorporates sensor data, assesses the vehicle's capabilities, makes decisions about its mission. You have to be able to deal with contingencies in an intelligent way, guidance, navigation, and finally trajectory following control. So I'm going to focus strictly on the trajectory following control today. And so what is control? Well, the term actually has many meanings and often varies between different communities. We're going to define control as the use of algorithms and feedback in engineered systems to alter system behavior. Feedback happens to be a basic mechanism but which all systems, whether they're mechanical, electrical, or biological, tend to maintain their equilibrium. So something like feedback and control is very intuitive, but again, for flight, there's some lessons to be learned. And at its core, it's an information science because we use information, both its analog form of sensors and its digital representation in computers. Examples include things like feedback loops in electronic amplifiers, fly-by-wire systems in aircraft, router protocols to control internet traffic, autonomous vehicles and robots. As I said, it is a very large field and I can't do it justice in 45 minutes, but we'll try to at least give you some basic lessons learned. So what is a control system? Well, a modern controller tends to sense the operation of a system. It compares that against a desired behavior that you specify, and then it computes some corrective actions based on the model of the system that you have and its response to some external inputs. And then, of course, you actuate the system to effect the desired change. So in a sense, the basic feedback loop that we've talked about is sensing, computation, and actuation. The key issues in designing controls is to make sure that the system is stable, and stable just means for any bounded disturbance, you have some bounded error. And that in addition, the system has some desired behaviors, such as you want some good disturbance attenuation. So in fact, if you have wind, you don't want the vehicle, you want the vehicle to attenuate the wind response to the wind and not to actually grow in that response. You want to be able to respond fast to any commands you give to the system. And there's others. So these properties are established in a variety of modeling and analysis techniques. As I said, it's a very large field. But there are certain things that are in common regardless of what technique you use, and they're just fundamental good practices. So one of the things that is absolutely paramount in order to design, and not only design, but more importantly, analyze the behavior of any vehicle system you're going to build, is to be able to do vehicle dynamic modeling and then simulation. You need to model the system so you can understand and then control its behavior. So what if I don't have a model, but I can still fly it? There's a number of people who have flown vehicles. Well, the problem is that you can fly it only in a very narrow range. Whatever it is that you can do at this point, what you do not know is where would the system go unstable, or if that instability is controllable. So any external input, any external disturbance, or any input made by the pilot can result potentially in catastrophic failure. So you do need models of your system, not to tell you that it works, which is important, but it's to tell you where things start going haywire. So how can you determine vehicle dynamics? Well, there are traditional methods. You can go to the wind tunnel, you can do computational experiments such as CFD. You can start even doing a little bit of envelope expansion, identify your system. But at the end of the day, you really do need to determine your vehicle dynamics over the envelope that you're going to fly. And then through flight test, you validate whether your model is close to what you think it is. And if not, you need to correct. But again, I can't emphasize enough that before you can do any control design and analysis, you really do need to have a vehicle model. Now, to create a vehicle simulation, you start with standard equations of motion, model of some vehicle subsystems, whether they be actuators, which typically can be modeled as a simple first-order transfer function, or as a propulsion system, which typically requires a little bit more complicated model. Then, as I said, you update this vehicle model and its individual components as the information becomes available. That constitutes your simulation. That simulation is being used both to design your control and, more importantly, to analyze your system behaviors. All right, so let's go back to just focus on control. So I mentioned feedback several times. Why feedback? Well, if you have a controller and you have a system and you have some reference, if you know your system perfectly, then you can design your controller an open loop that will, for any command signal, it will provide appropriate actuation. The system will follow that signal perfectly. However, we do not know the system dynamics perfectly. And we have some external environmental disturbances, which means you need feedback to deal with that error between whatever it is that you're commanding and whatever it is that you need your system to respond. So hence comes feedback. And the goal of this feedback is stability, performance, and robustness. And we'll cover those in future slides. So this is a very basic diagram of your feedback system. You have a controller that consists of two elements. One is a feedback controller C that acts on the error between your reference and your system response. And you have your feed-forward part of the controller, F, which is actually something that you can use to shape your desired commands of the system. This is called a 2-degree of freedom control system. Then you have your plant P. That is your system. That includes your sensors and includes your actuators. You have some disturbances that enter at the plant input. Those are try to drive your systems from the desired state. So whether there are winds, whether it's turbulence, all of those are your internal disturbances. And again, they're going to drive you away from your desired trajectory. You want to be able to reject those. You also have measurement noise in your sensors. That's going to corrupt the information about your system state X. And so your output of the system Y is going to be a combination of your system state plus the corrupted information through noise. And so for the duration of the talk, we're going to make an assumption. We're going to assume that our feed-forward element, our shaping element, is going to be 1. And so we're going to focus strictly on 1 degree of freedom systems. Now, the nice thing is actually the decomposition between F and C in practice is very doable. You typically design your feedback system with your controller C for all the properties that you want. And then you can design your F, your feed forward, to shape the response. And as I said, that comes with experience and that adds a little bit extra complexity. And so we're going to leave that out for the purposes of this conversation. So let's talk about properties of feedback. Well, one of the most important properties is its robustness to uncertainty. As I said before, we don't know our system perfectly, so we'll have some uncertainty. So our controller somehow has to deal with that uncertainty. So generally, feedback allows a system to be insensitive both to external disturbances like wind or turbulence and to variations of individual elements. Again, it's uncertainty of your system dynamics. It's something can change. For instance, your center of gravity can change. Your center of pressure can change. Those all introduce variations in your system dynamics. The goal of your feedback is that you become insensitive to those variations. The other aspect of feedback is that you can design the dynamics of your system. So for instance, if your system as designed does not behave in a manner that you would like it to behave, then through feedback, you can change those dynamics. Of course, there's limits to everything, but again, that is one of the properties of feedback, is allowing you to change the dynamics. There's, of course, no free lunch. There's a trade-off. There's potential disadvantages. Feedback can actually cause a stable system to go unstable. It can introduce unwanted noise into the system. Remember we said there's always noise in your sensors. Well, through feedback, we can potentially amplify that noise. So for all of these reasons, of both advantages and disadvantages, substantial portion of our study of feedback systems is actually devoted to developing understanding of the dynamics and the mastery of techniques of dynamical systems. Hence, let me circle back on why I said that vehicle models are so important, because you are trying to study its dynamics. And the one message to keep in mind through the rest of the talk, there's no free lunch. There's always going to be a trade-off between different quantities and qualities that we're trying to impact. So as I said, feed forward very briefly. Why is it something you need to keep in the back of your head? And if you're going to do this, go to literature to figure out how to do this right. Feed forward is useful in shaping the command signal, but it requires good system models. So that's what the feedback is doing. It's giving you that system model that then feed forward can use. So let's talk about now controller design. So what are the criteria? Well, there's a general procedure. So we're going to design controller C, remember it's our feedback controller, in order to achieve low sensitivity to some disturbances. We want low sensitivity and small injection of measurement noise. We want high robustness to system variations, which means uncertainty and variability in plant dynamics. And then we would design, if it was a 2 degree of freedom controller, we would design F to achieve that desired response. With the control theory itself, it's a formal science, and there's at least 60 years or not, if not more, of theory associated with it. But in general, what it does is control theory provides you a very rich collection of techniques to design a controller, and these techniques exist both in time domain and frequency domain, to analyze the stability and the dynamic response of complex systems, and then to place bounds in the behavior of such systems. And we do that by analyzing gains of linear and nonlinear operators. So essentially, design and analysis is very much an iterative process. You design a controller, you analyze it. Typically, it's not perfect to reflecting what kind of behavior you want, and you go back to design, and so again, it's an iterative behavior. So as I said, the 3 goals of your controller design and then the analysis to confirm that is you need, first and foremost, stability, which means bounded inputs produce our bounded outputs. Performance, which means you wanted some kind of desired response. You specify that response, and you can specify it in frequency. You can specify it in terms of time domain. The main problem with performance is disturbance rejection and command following. And then there's robustness. And robustness is, how do I keep both stability and performance in the presence of known dynamics? So in other words, I check my stability in the presence of uncertainty. And I need to check that stability for a set of systems, because uncertainty means that the system, think of a system as having different parameters, different CG locations, for instance. Each time there's a new location, it's a different system. So you're really checking stability of a set of systems. And again, as I mentioned before, if there's no uncertainty, there's no need for feedback, but we always have uncertainty. But there's always need for feedback. So as I said, if we're going to, for a moment, neglect our second degree of freedom and our shaping of our reference signal means that our controller F is going to equal to 1. Then we have to look at the control analysis for our controller, right? We're going to say we have specifications. So what kind of specifications are we looking for? What are we designing for? Well, we typically we have specifications in time domain because, you know, our systems, when we fly it, we don't feel the frequency domain response. We really feel how it responds in time. We know that if we pull back on a stick, how quickly we gain the whatever, let's say, pitch angle that we want. How much overshoot do we get from the desired value? How long does it take it to settle to that steady state value of our desired, let's say, attitude? All of these have specifications. So the things I mentioned, so we have the rise time of a system, the overshoot of a system, the settling time, and then final steady state value, and how much error do we have in gaining. So there are very direct relationships between the time domain and the frequency domain. And we're going to focus on the frequency domain, frankly, because it is a more classical way of analyzing systems. It is a little bit less complex, and it's something that if you understand how the systems, both for design and analysis in the frequency domain, it then transfers nicely to time domain and more sophisticated methods. And so we're going to, as I said, we're going to focus on frequency domain. So for example, well, you said, okay, you said time response. Well, how the heck do I translate that into a frequency domain? Well, as I said, nicely, there's a relationship. So for example, rise time is related to a system bandwidth, how fast the system can respond. And in the frequency domain, it's roughly proportional to the inverse of the crossover frequency. The overshoot and the settling time, or the oscillatory response, is also a function of system damping and frequency. So in the frequency domain, again, it's one of those key ideas that form the foundation of control. Until about 1960s, all control theory primarily dealt with the frequency domain. And we're going to focus on linear, single input, single output systems. Now, if you understand those systems, then there's equivalent analysis that exists for multi-input, multi-output systems. But the basics are really something that needs to be understood in single input, single output. And so the idea of frequency response is to characterize a linear time invariant system by its response to sinusoidal signals. The idea is that for a linear system, if you inject a sinusoid for a given amplitude and frequency, what you're going to get out, if it's a stable system, is a sinusoid of the same frequency, of the same amplitude. It's just going to shift in its phase. The nice thing about frequency response also is you can take a very complex system, and it's easier to see its properties in a frequency response. So it's an alternate way of viewing the dynamics. It's also easier to take a look when you're looking at sensitivity to uncertainties. So another example is, if we look at a linear system, we know that a linear system is stable if its characteristic polynomial has roots in the left-half plane. Well, that's great, but A, we need to derive the characteristic equation, which may be not that easy, especially if you have complex systems. And then you have to find the actual numerical roots. Now, if you start going beyond second-order systems, you start getting into solutions of those equations are numeric. Well, not only that, assume you can find those solutions. What it doesn't tell you when you solve those equations is how to modify your controller so that you can alter that behavior. How you can alter the position of those roots of that characteristic equation. Remember when I said we alter dynamics of the system? Well, this is it. Frequency response allows you a more intuitive way of doing that. Moreover, when we talk about stability, it's in some respects, it's a binary definition. It says either the system either stable or it's not. Well, in practice, we really are interested in degrees of stability. And again, frequency response allows you to do that. Just for your information, a key in frequency response is Nyquist stability criterion. We're not going to cover that, but again, it's something that I like for you to keep in mind as you go and explore this topic a little bit on your own. So let's get back to closed loop analysis. So we're going to take an advantage of this idea of a transfer function. And a transfer function is simply a system input-output representation that is done, it takes advantage of a Laplace transform, and so we end up in a frequency domain. And that simplifies a lot of our operations. So again, given the diagram of our basic feedback system, the way we're going to start with the analysis, we're going to derive a transfer function for each block in this block diagram. So there's a transfer function for the controller C, there's a transfer function for the plant P. And then once we have our transfer function, we're going to then simulate and see what happens as we combine these transfer functions together. So if we trace this path of the signal from different inputs to the system, and here we have three. We have the reference signal R, we have the disturbance D, and we have noise N. To the system output Y, we end up with several transfer functions of interest. We end up with a transfer function that describes the relationship between output Y and our reference command R. We have a transfer function that talks about, describes the relationship between our disturbance and our system output, and also between our noise and the system output. If you notice, all three of these transfer functions have one thing in common. Their denominator. The denominator, the 1 plus P plant times C control, is called a loop transfer function. And all of our frequency analysis can be done in terms of this loop transfer function L. So first we're going to look at stability. So as I said before, we really are interested in the margins of stability, not on the either system is stable or not. That happens to be governed by the evolution of the loop transfer function as our frequency goes from 0 to infinity. So as the frequency increases, that's the evolution of the function. The stability margins are directly related to the gain and phase of this loop transfer function. So the stability margins of the entire system are related to the gain and phase of this loop transfer function. One of the very useful representations of frequency domain is a Bode plot. Bode plot happens to be done in two curves. One is a gain and one is a phase, and it's done on a logarithmic scale. And logarithmic scale because then it looks linear and we can take advantage of certain other aspects of it. So if we introduce the concept of gain and phase margin, so gain margin, GM, as you'll see on the plot, it really is how much the controller gain can be increased before we reach the stability limit. So if we double our gain, is our system still stable? Remember when I said that feedback can destabilize the system? Well, if we increase the gain too much, that's precisely what can happen here. And there's a phase margin. And the phase margin is the amount of phase lag that's required to reach the stability limit. So in a lot of cases, the phase margin starts coming in equivalent to a time delay margin. So think of having some time delays in the system. How much of that can we inject before we start going unstable? So rule of thumb, reasonable margins. Gain margin varies between 2 and 5. And phase margin that you're looking for when you're designing, somewhere between 30 to 60 degrees is what you're really looking for. As you note, again, let me point out on these plots, note that the frequency response looks fairly linear, especially in gain and phase. And the frequency itself is going from 0.1 radians per second to 1 and continues on. All right. So another idea that's also very important to understand the behavior of the system as a whole is this idea of a sensitivity function. And sensitivity function is simply defined as 1 over 1 plus loop transfer. And there's an equivalent complementary sensitivity, which essentially is your closed loop system. That's your T. That's PC, your controller 1 over plus. If we go back and look at our equation again, that gives us system response in relation to 3 different inputs, those reference command, disturbance, and noise, we note that the response to a commanded input is governed by our complementary sensitivity function. However, the response to disturbances and response to noise is governed by a sensitivity function. So if we want to be able to track commands, we care about our complementary sensitivity. And if we care about rejecting disturbances and rejecting noise, we care about the size of our sensitivity function. Another condition that's extremely important is how well are we rejecting, or how well can we deal with the uncertainty in our plan. So the relationship of delta P is representing the uncertainty in our plant, the variation in our plant dynamics. And if we look at the relative magnitude of just how much uncertainty we can deal with in a plant, that ratio has to be less than 1 over the magnitude of our complementary sensitivity function. So all of this has certain implications for our design. That means that the variation in our plant dynamics can be large for those frequencies where our complementary sensitivity function is small, but those variations have to be smaller for the frequencies where T is large, right? So think about it, typical commands are lower frequency, noise are high frequency. So at lower frequencies, we want T to be large, and we want T to be small at high frequencies so that our noise is not amplified. Because remember, T is also our closed loop system. Let me see what else. Disturbances can be lower frequency, for instance, constant wind. It can be higher frequency. It can be turbulence. There's system dynamics that we may not want to excite, such as unmodeled or structural dynamics that are typically higher frequency. So again, there's always going to be the trade-off between what happens at lower frequency, what happens at higher frequency, and we'll have to balance that response. So there are some constraints on the design. If we'll come back here for a moment, what do we say? We want S is our governs response to disturbances and noise amplifications. So it's advantageous to have small values of sensitivity function S. And it's also advantageous to have small values of complementary sensitivity function T to allow for large system uncertainty. However, we do have a limitation. We have S plus T must equal 1. So your stability and robustness basically have to be balanced. That's your trade-off. So the S and T cannot be made small simultaneously. That's where the trade-off starts coming in. And if you start looking at just the definition of the functions and what they will look like in the limit, so your sensitivity function S is going to be typically small for small frequencies and close to 1 for large frequencies. And your complementary sensitivity is going to be close to 1 for small frequencies, the opposite for as omega goes to infinity. So there's a fundamental conservation law in controls. It's called the Bode interval. Essentially, it's a waterbed effect. What it tells you is that the sensitivity function can decrease at one frequency at a cost of increasing at another. That means that disturbances of some frequencies can be attenuated only if disturbances of other frequencies are amplified. So you have limitations on achievable performance. Now the question is, can S be made small over a large frequency range? And of course, the usual answer is, it depends. Let's discuss what it depends on. So what are the fundamental performance limitations? So there's two things. One is how quickly can a system respond to change in your command? And two, how well can you reject your disturbances? So some of the factors that are going to limit your performance: measurement noise, actuator saturation. How fast can your actuators respond? Because saturation can happen both in position and in rate, and your system dynamics. So for example, fast response requires controller with high gain, which means fast closed loop system. However, measurement noise is going to be amplified and fed into the system, which means high frequency variations in your control signal will potentially lead to saturation. So high gain for fast response will basically induce higher noise, potential control saturations, and high frequency variation in your system response. So think of dithering, and which is not a good response for the system. It can make you sick, for example, if you're flying. It also not particularly good for your hardware, because if your control actuators are responding very rapidly, that means that you're diminishing their life, regardless of whether they're hydraulic or whether they're electric. In fact, you're going to burn out your electric motors if you have this very high frequency control signal response. So measurement noise and actuator saturation gives you a bound on the high frequency gain of the controller and on the response speed. In addition, depending on your dynamic properties of the system, you may end up with severe limitations. There are some systems that are inherently difficult to control, and some systems are impossible to control. For example, fast closed loop system is required to stabilize an unstable pole, and that response speed needs to be matched to an unstable pole. Also, if you happen to have a right-hand plane zero, which means you have non-minimum phase response, an example of that, if you're using an elevator to control the height of your vehicle, your initial response of the vehicle is going to be to dip as opposed to go up, if that's what you're trying to do. That's your non-minimum phase response. Well, if you have that right-hand plane zero, you're essentially going to be limited in your response time, right? So unstable poles are going to limit your system response. Right-hand plane zeros are going to limit your system response. And you say, okay, well, what do you mean system is impossible to control? Well, for example, if your actuators are not fast enough to provide the required speed to stabilize your system for that unstable pole, your system is impossible to control. So you'll have to redesign the system. That's just an example of a limitation. So, as I said, given all those limitations and the idea of sensitivities, we're now going to briefly discuss some of the typical control and design methods and some observations about them that you'll see are either used in some controllers for UAVs or been used throughout control for flight vehicles. The first one is your standard proportional integral derivative control, PID. The standard version of the controller is given as 3 parts. The first part is your proportional gain on an error between your response and your desired behavior. Second one is integral, and the third is derivative. So essentially, the proportional part acts on the present value of error. The integral part looks at the current, basically past error, so it looks at what happened, your history of the past. And the derivative can be interpreted as a prediction of your future error based on some linear extrapolation. So you're looking at now, past, and future. Some practical observations. There tend to be a large initial peak in the control signal that's caused by a derivative of the reference signal. You can always introduce a weighting on your reference signal R in the proportional and derivative terms that will minimize that initial peak. The implementation of pure derivative doesn't happen in practice. It's very noisy. Typically, derivatives it's implemented as a derivative that's filtered by first-order low-pass filter. And since you have integral action, it's very important to have an integrator anti-wind-up protection. There are many ways to tune a PID controller. One of the advantages of PID control is that you really don't need to know your system model, ideally, right? Because it's not really a model following control, except that, and that's why the reasons that this control is extremely popular in industrial applications, especially in chemical processes. However, in flight, we really can't tune the controller in flight, at least not for stability initially, right? So we still need some kind of model. And the control techniques that when PID's been used in flight, it really was based on model. And pole placement, for instance, is one way of doing that, using characteristic polynomials. And then you can start tuning slight variations potentially in flight. But again, that is not necessarily the most preferred way of tuning something while doing it in flight. Good starting references for how do I tune a PID controller is provided by Astrom. If you were given in the references, but again, this is something that if you want to do PID control, I highly suggest that you find papers and books by Astrom. The next step in the classical control, beyond PID, is we start looking at loop shaping. Remember I said frequency response, and frequency response using allows you for more complex dynamics and deal with them a little bit simpler. So classical frequency response loop shaping is something that was developed from 1920s through about 1950s was the way of doing things. And here it's lead lag controller is your standard classical controller. The idea is that you find a controller so that the loop function has certain desired properties. Your lead compensator, as provided here in an example of the lead compensators are given in a frequency response on the right, is used to improve stability margin of the system or to increase the crossover frequency, which means increase the speed of the response. It depends on 2 parameters, B and N. N is always greater than 1, and the plots show you what happens for different values of N. Interestingly enough, N goes to infinity. This very much resembles a response of a derivative portion of PID control. The complement to a lead is a lag compensation, which is used to increase the gain of the loop transfer function as at low omega. So basically, we want to improve our command following. And so that requires, that also implies that we're going to improve our attenuation at low frequency disturbances and reduce our tracking error. And again, something very similar is shown on the right. What happens when this parameter M increases, and when M goes to infinity, this very much looks like the integral action of PID. So as I said, this is closely related to PID. We're going to very quickly switch to the next one. And so starting about 1960s, the control theorists started looking into a different system representation. They started looking at a system dynamics modeled in state space form as opposed to in frequency response. So instead of a transfer function, you're now looking at state space form that's done as far as x dot equals your AX plus BU, where B is your control effectiveness matrix, and Y is your output, and in this case, simply Y is equals to X. So we have full state feedback. So for linear feedback, the control signal U that's given as some negative gain on K on your state X, and some gain on your command signal, results in a closed loop system, as you see there. Now, if we're interested in basically getting or that control of that system, one of the most used methods is something called linear quadratic regulator, LQR. Sometimes it's referred to as LQ, but essentially it's a linear quadratic regulator. We now bring this idea of optimal control, we're marrying it with flight control, and essentially what it's doing is it's trying to minimize the performance index. It happened to be quadratic, but it's trying to minimize it along all possible trajectories of the system. All possible trajectories of the system has implications for system stability. So essentially we're optimizing, or we're trying to minimize and balance between our states, X, and our control U, with certain conditions on the weighting matrices. What's interesting is that we can find an optimal trajectory is generated by this controller U that has a very simple form. It is simply a gain K times our state. And we solve for that gain K by solving algebraic Riccati equations. This is something for those of you who use MATLAB. It's a very simple LQR command. Unfortunately, a lot of cases, I've seen people use commands without truly understanding what's behind the algorithms, and that potentially can lead to a lot of problems. So let's talk about, well, okay, so I have these two weights, Q and R. How do I choose them? What do they really mean? Well, we choose Q and R. First of all, we start with them as to be diagonal. So you're penalizing strictly the states or strictly the controls. You're not worried about the cross-coupling between them. And what you're looking for is a relative penalties on the state and the control. So it's not the, as I said, it's not the absolute value of Q, it's not the absolute value of R, or the elements are off, but it is the relative values. And so what you're really doing is making a trade-off between attenuating disturbances and amplifying measurement noise by balancing this deviation of the state from zero and the control effect. That's what this minimization index really does. Why it has been very popular is because what you get from this optimal linear regulator is a guaranteed gain in phase margins. Now, it's important to point out, you get these guarantees at the plant input only, but what that implies is you're guaranteed phase margin of at least 60 degrees. And recall, we wanted somewhere between 30 and 60, so 60 degrees is great. And we get infinite gain margin, or to be more precise, if our system is open loop stable originally, then our gain margin really is infinite. If our system is open loop unstable, then our gain margin is, the system is then going to be stable for gain between half of what you designed and infinity. So again, this has extremely appealing stability characteristics, and which is why people use that. So what happens if you don't have full state feedback? Well, you can then introduce observers, and unfortunately that starts destroying the guaranteed gain and phase margins. But there are techniques known as loop transfer recovery, which essentially allow you to approximate these stability margins under certain conditions, and again, recover these margins. So again, it's a very widely used and appealing technique. Another widely used technique in flight control is something called dynamic inversion, or in some textbooks, it's referred to more general form as feedback linearization. It's popular because it allows you, so for the previous methods we talked about, these have been all linear systems. So you have your plant, you have to linearize it, then you design controllers. In this case, we have nonlinear systems. We still need a model, but we can essentially invert that model and then use a single linear controller across the entire flight envelope. So no gain schedule. In some respects, dynamic inversion is a special case of model following control. The issues with dynamic inversion, it requires exact knowledge of your model dynamics to achieve good performance. So robustness is really a key issue since we don't know our model completely. And even if we can invert the model, we're only approximating, so our model plus our aircraft, actual aircraft dynamics, only ideally approximating an integrator, and only within the bandwidth of the actuators. But if we design our linear controller astutely, and it is the term that's been used in literature by people who've done this successfully, then we actually will have good robustness, and we will have good performance of this. And again, I'm providing some references in the back to give you a better idea of just what all of this does if you choose to use this formulation. So these are all methods. They've all been successful. However, there's another methodology that's been around for a while and has been extremely successful over the past at least 20 years. And I'm going to talk about this particular one, this particular methodology, but in general, I'm talking about adaptive control. So adaptive control is something that's extremely useful in dealing with varying model parameters, but more importantly, with faults and failures. So it provides you extra measure of robustness and safety if it's properly designed. And I can't emphasize enough, proper design. Not all methods of adaptive control are equal. Not all methods are appropriate for flight in safety critical systems. So I'm going to give you a quick overview of one particular methodology that I've helped grow and develop, and it's L1 adaptive control. And that's something that has flown on UAVs, but more recently had several flight tests in fully manned flight vehicles with a number of faults and failures. And as I said, it's been showing itself to be very successful in flight. One of the things that it allows for, it is a robust control, adaptive control architecture that allows fast estimation schemes. So you can estimate your uncertainty very quickly. And even more importantly, it allows you to a priori quantify transient and steady state performance. This is the only technique that allows you to do that in adaptive control. Most adaptive control looks at what happens asymptotically, what happens at the end, sort of as everything becomes steady state. Well, in flight, nothing is particularly steady state, and not only that, you can unfortunately bounce off the ground 3 times in your transient behavior before you achieve your stable steady state. So as I said, being able to predict your transient behavior is extremely important for your controllers, be it robust control, be it PID, or be it adaptive control. And so the way we typically use adaptive is we design a robust baseline controller, and then we use adaptive as an augmentation to provide that help when things go haywire. I'm not going to go through the actual architecture other than to say there's a standard estimation loop and the control loop, and then the control signal is generated, but only within the limits of the bandwidth that your actuators can actually provide. So in summary, I want you to remember, if nothing else, that there's always trade-offs between performance and robustness. The design challenges for the controllers include disturbances, measurement noise, system variations, or system dynamics themselves, sensor resolution, actuators. The criteria for control design: remember to attenuate the effects of your disturbances. Do not amplify noise too much. Do not excite high frequency unmodeled dynamics. Make your system as insensitive as possible to variations in your system parameters and dynamics. Make your system state follow your reference input at your command, and make it robust to failures. And at this point, I'm going to display this slide of references, and I'll take any questions in the time that we have.
Thank you so much, Irene. Incredibly informative and a lot of great information and references that our teams can take back. I'm sure this is one that they're going to need to pause many times along the way to rewatch. So some of the questions that we have coming through is, you had mentioned that we do not know our system dynamics perfectly. What is the metric for how good the model can be, or can I know in advance what is good enough?
That's an excellent question. What's good enough is something we always struggle with. Typically depends what phase of flight you're in. If you're just starting and you have something that looks like, so let me back up. A lot of times, especially when we're designing vehicles for go fly, the configurations are rather unconventional. So the question of what's good enough, it truly is still an open question. If our configurations look more like conventional configurations, whether it's a helicopter or whether it's a standard airplane, then we have pretty good idea of how close our linear models are to our real models, just because of similarity configurations, and that's available in literature. For some of the new ones, we really don't know. So the way I would approach designing controllers for these very unusual configurations is you create a model, you use the best techniques available to you, whether it's high fidelity CFD or whether it's wind tunnel, but you create a model, and then based on your assessment of how good you think that model is, I would start introducing uncertainty into my system and then check how good my control design is to deal with those uncertainties. For instance, if all I have is just a linear model from my equations of motion and I really don't have a good idea of what my aerodynamics are, then I would start introducing very large uncertainties in my aerodynamics to see how good I am and design for those uncertainties. And then I would start flying at a very benign conditions and start comparing how good my model is to what it is that I'm seeing in flight. And very slowly then start expanding my envelope. Again, always comparing what my model predicts versus what I'm actually seeing in flight. Again, that's the best answer I can give you for how do you know how good, whether it's good enough.
Mm-hmm. Certainly. And are there linear single input to single output analysis sufficiently robust for distributed propulsion systems?
Excellent question. I would claim that the answer is probably no. The single input, single output is sufficient. It's the first place to start, because if it doesn't work for single input, single output, it's certainly not going to work for multi-input, multi-output. If you understand, as I said, single input, single output, then the next step is to go multi-input, multi-output. Any number of references that I gave here will address that. If not, there's a number of others, but again, I would absolutely start with single input, because if it doesn't work for that, it's not going to work for the next. And then there's singular value analysis and structured singular value analysis that you would do for multi-input, multi-output systems that, again, are frequency-based and similar to what I've showed you for single input.
Okay, great. You also mentioned noise, or a sensitivity to noise, when discussing disturbances. GoFly, we have a criteria for these conditions. Do we need to plan for disturbances greater than specified?
So noise and disturbances are related but not the same. The disturbance criteria that's been specified is sufficient. However, the noise comes in strictly from sensor measurements, right? So the noise, it becomes how good are your sensors need to be in order to provide you the right performance. And that question can be answered by, if you're trying to minimize your noise, can you still reject the disturbances as being specified in a GoFly criteria? If the answer is no, then you have to get better sensors. Because again, they happen to be in a similar frequency range, then your sensors will preclude you, your sensor noise will preclude you from being able to appropriately deal with those disturbances. But those disturbances, those are what those are. That's your external requirements. And as I said, sensors and the noise they inject are part of your system, and that's the one thing you have control over. That's what you have to start changing if you have to.
Okay, so as you know, we are now in phase 3 of the competition. So some of our teams are fairly far along in their design. So their effectors are mostly done. What are the key questions that a team might need to answer right away to know if their system dynamics are acceptable, or if they need to make changes?
They need to be able to, look at the model of their system, and especially since their control effectors are already set up, you can run bench tests to get a high fidelity model of your effectors. You can put that in your simulation, and then you can see if they're sufficient for the kind of command following and disturbance rejection. They're the criteria for GoFly. If the answer is no, then you need to ask yourself, is it because my control design is not good enough? Or because I actually reached the fundamental limitations of my hardware? And that I cannot answer for each team, that each team will have to look at it themselves.
Mm-hmm. And then last question that we have right now is, in your experience, what magnitude of changes in gains are significant? Will there be nonlinear impacts on the system dynamics for small changes in gains?
No, so if that happens, that implies that you have a highly nonlinear system, and that means that the linear methods are either inappropriate, or when you use linear methods, typically the way we design is that we linearize at different points in a flight envelope, and we design controllers for each one of those points, and then we gain schedule. And so typically we do that at fairly far along the envelope because we have reasonably linear systems. If our system is highly nonlinear, as would be in this case, then those points where you design controllers have to be much closer together. So for small change in your small change in gain, you would end up with essentially a different controller to deal with that nonlinear behavior. It would be different than what was the step before. If that answers the question.
I think that's certainly helpful, and we will ask our teams to follow up should they require clarification. So Irene, thank you so much. We have gone over the hour, so I want to thank you for your time and invite Gwen back for a few final comments.
Thank you.
Thank you, Dr. Gregory. The master lecture that you just gave is incredibly informative and exactly the type of information our teams need to incorporate into their flyers. So thank you very much for that. We are very pleased to be having several upcoming master lectures. So to all of our teams, stay tuned for that. And just want to end with a very big note of appreciation for Dr. Irene Gregory from NASA for today's master lecture. Thank you all.
Thank you.
Thank you.